All right, so today we're going to look into the fundamentals of voltage, current, power, and energy. And we'll also look at a table for unit prefixes. All right, so let's bring up our, not that, this one. Okay, common two-terminal devices. Okay. All right, so broadly classified in electrical engineering and electronic engineering, we classify our devices into two broad categories known as sources and loads, right? Anything that consumes energy is a source, is a load. Anything that supplies energy is a source. So other than power supplies, all other devices that we encounter, they're all loads. Okay, they're all consume energy. They all consume energy. And when we say consume energy, well, there's work being done. Energy follows the law of conservation of energy. The process follows the law of conservation of energy, which is the first law of thermodynamics. Energy is neither created nor destroyed. It's always converted from one form to another. All right, measurement. So when the first measurement meters came out, the symbol was something like this. This means this is a measurement meter. Okay, measurement meter. That arrow, which is at an angle, signifies that, or it notes the movement of the dial, analog dial. So the first meters were, of course, analog, and hence we had these kind of symbols to represent them as analog dials, or the movement of the dial. If it measured voltage, it was known as a voltmeter. If it measured current, it was known as an ampere meter or an ammeter for short, just ammeter. If it measured resistance, it was known as a ohm meter. So pretty much it was named, the device was named after the units for the quantity that it was measuring. Then came along a meter that could measure all of these quantities all in one. So it came to be known as a multimeter or a multimeter because it could measure multiple quantities. Okay, multiple quantities as in voltage, current, and resistance. And it's a multimeter. And then came along digital versions of these meters, to be known as digital multimeters or DMM for short, DMM. And so in the lab, I'm assuming you already have experience with the digital multimeters. Yes, 45. On the 8 lab benches behind us in this room, we have one digital multimeter on every single bench. There's actually two on every single bench. The small instrument on the far right is a source meter, very expensive device. It can function as both a source as well as a meter, hence the name source meter. All right. Unit prefixes. So in any scientific field or in any engineering field, we deal with a wide range of values from the very, very small to the very, very large. In everyday life, you are familiar with many of these terms, whether you're an engineer or it doesn't even matter whether you're an engineer or a scientist or a researcher or whatever. In everyday life, we use these unit prefixes. For instance, or for example, the wireless band or the band, frequency band of your wireless router. Any guesses on what that number is? 5G, but well, 5 gigahertz. That 5G is a little different. So I'm going on a little bit of tangent. When the first mobile networks came out, this was in the 80s, Motorola had that network in New York City. And then the first data networks came out. They were just simply known as first generation, never said anything about it. And then the first internet network came out over wireless cell phones. They called it the second generation, hence 2G. So the first internet networks that came out of the smartphones, they were known as 2G. After that came the third generation, so 3G, fourth generation, long-term evolution, LTE, hence 4G, LTE, and now we are, they say, supposedly fifth generation. But fifth generations, more often than not, sometimes works like 3G in many places. So the promise of this technology is that you get a higher speeds as the generation evolves, like hence the name LTE. But that's not always true, or that's not always works as intended in real life. Anyway, that's the 2G, 3G, 4G, and 5G. The bands for the wireless router are 2.4 gigahertz and 5 gigahertz. Giga, as you can see here, 10⁹9. Okay, 10⁹9. Tera is 10⁻12, mega is 10⁻6, kilo is 10⁻3. And on the other side, we have milli, micro, nano, and pico. From your electronic devices, whether it's your cell phone, your tablet, or your computers, we are familiar with the operating frequency of your processor. We're also familiar with some idea of what the memory or the RAM is inside of our devices, but more specifically, the storage of our drives. Right? Storage drives nowadays are commonly outed at least 256 GB of data, or at least 256 gigabytes of data. That GB stands for gigabytes of data. Processor frequencies are in the gigahertz range, typically, 1.5 gigahertz and above. Memory, the random access memory or RAM memory, is typically 8 gigabytes or 16 gigabytes or higher. And so again, those are all the giga range. When I got my first computer back in India in 1999, it had, and for that time, it was, I would say, it was quite top of the line specs in that sense for a student. 128 megabytes or MB of RAM and 4.3 GB hard drive, which was a really big deal. Felt like an ocean at the time. It's like, what are we going to use all this space for? Well, now 4 gigabytes is not even enough RAM memory for devices. So that's how far we have come. I still remember the first digital camera I ever purchased was from Circuit City for like $200. 3 megapixel, again, 3 megapixels because the resolution of the camera sensor was 3 megapixels, 3 million pixels in there. And for $100, I purchased a 128 MB, not GB, 128 MB of storage. That was like $100. I think I still have it somewhere in one of my boxes, just to show how stupid amount of money that we spent at that time. Anyway, on the next page, I have a comprehensive table that I expect every student to memorize. I'll ask this on a closed book, closed notes quiz. Not really, even I don't have this memorized. We are all familiar with the middle of the table right here. Those are the ones that we deal with in most everyday life, in our academic life, at least, as an engineer. We're familiar with multipliers on the left. Kilo is 10⁻3, mega is 10⁻6, giga is 10⁻9, tera is 10⁻12, and so on and so forth. I've heard about the data that they collect, that these agencies collect on us, like not agencies, like any store. If you visit a store website for a few minutes and you're just browsing through, apparently it generates like gigabytes of data just on like few minutes. And so a few years ago, I was taking like a business class, and the professor was talking about some research they were doing in conjunction with Target. And Target wanted some data to be analyzed and said you could hand over 2 minutes of data, and that was like a petabytes of data, just 2 minutes. And that's like just ungodly amount of information that they collect. Anyway, let's talk about the right side, right? Yeah, milli, micro, nano, pico, just to give you an idea, a visual idea of how small that is. We all familiar with centimeters. Centimeter is, well, is 1/100 of a meter. 100 centimeters equal to 1 meter. 1 centimeter is something that we have all used because we're familiar with our rulers, with our scales. You divide 1 centimeter into 10 equal parts, you get 1 millimeter. So 1 millimeter is something you can still visualize, right? If you take that 1 millimeter and divide it into 1,000 parts, we get 1 micrometer. 1 micrometer, noted by the Greek letter mu, is more commonly, or in technical circles, is known as 1 micron. 1 micron. So if you ever hear me say the words micron, that's what I'm talking about, 1 micrometer. This is also the reason why microchips are so called, because the earliest microchips were basically, you cut them out from a single silicon wafer, and the feature sizes on the order of a few microns, hence the name microchips. Okay, it's an actual semiconductor company in existence by the name of Micron Technologies, Boise, Idaho. And then if you take 1 micron and you divide it into further 1,000 parts, you get a 1 nanometer. That's small. And the current feature size of microchips nowadays, the state-of-the-art microchips, are on the order of 3 to 4 nanometers. Okay, so small we can't even imagine. The reason we talk about them and the reason we need to learn about them is because the capacitors and the inductors that we deal with are on the order of milli and micro. More typically in real life, it's actually nano and pico and even femtofarads, very, very small. Okay, microfarad capacitor is actually really big in electronic devices. Okay, so most capacitors and inductors are in this range. All right. And on the other side, we have like high frequency devices that are in the gigahertz and the terahertz range. Broadcasting frequency signals starting from AM radio stations, which are in the kilohertz, FM radio stations in megahertz, television stations again in the high megahertz, and then you have the satellite and terrestrial communications in the gigahertz and terahertz range. So really, really high frequencies. Just as a engineering knowledge, wireless broadcasting frequencies, well, wired or wireless broadcasting frequencies are tightly controlled by the government of every country. This is like precious spectrum because this is a finite resource that is only awarded to a fixed entity, specific entity. So if 640 AM radio station is broadcasting at 640 AM, no one else is allowed to use that particular frequency. Otherwise, you would have interference. So 101.7 FM, broadcasting at 101.7 megahertz, no one else is allowed to broadcast at that frequency. Otherwise, it causes disruption. You ever hear of wireless jamming? Like wireless jamming is simply you take the operating frequency and you just broadcast noise at that frequency and you're easily able to jam your signals. So it's very easy to disrupt a Wi-Fi in your residences. It's easy to disrupt Wi-Fi cameras. Criminals or criminal actors can simply have a jammer. A wireless jammer is nothing but a transmitter that broadcasts at a particular frequency. You set it at 2.4 and 5 gigahertz, jams all the signals, nothing can go through. It's like cutting an actual wire. It's that easy to do. Okay, enough scaring. Let's come back here. To give you an idea of how big mega and a giga is, mega is a million, 10 raised to 6. All right. So let's use the concept of time. Take a wild guess as to how much is 1 million seconds in days, weeks, months, or years. 3 months, 3 years. That's a good guess. Anyone? Any other guesses? No one else wants to step up. There's no penalty on it. Yeah, feel free to speak up. It's fine. 50 days, that's a good guess. 20 days, that's another good guess. Anyone else? 20 days? 31 years? Not quite. It's 11.71 days. How much is 1 billion seconds? And now it's 30 years. It's actually more than 30 years. It's 31 point something years. That is the difference between a millionaire and a billionaire. A millionaire could spend $1 every second and would run out in less than 2 weeks. A billionaire could spend $1 a second, would not run out for over 30 years. That's how much money Bezos has and everyone else, the billionaires. So how much is 1 trillion seconds? This should be easy to figure out now. 31,000 years. How much is the federal government deficit? It's over $30 trillion. The deficit means the government has borrowed that much money to pay for services and infrastructure and everything. And now you're paying that money back. So the federal government has a deficit of over $30 trillion, meaning if they start paying $1 a second now, it'll still take them over 90,000 years to pay it off. Not to get into any of that, but just this is the world that we have inherited and you're going to be inheriting in a few years. So that's something to think about. All right. So anyway, as I said, the reason we talk about these is it makes our life easy, right? We use multipliers. Instead of using 31,000,000, just write in, whatever our prefix is, 31M, 31 N or tera or whatever. Quick note, most of the unit prefixes on the left, the ones that use uppercase letters, and the ones here use Greek letters. Okay. And so, well, they use Greek letters with the symbols, except for this one, micro right here. They just use the lowercase alphabets. But these are all Greek. Femto, atto, zepto, yopto, same thing over here. All right, fundamentals of energy and charge. We're all familiar with the structure of an atom. Atom comprised of nucleus. Nucleus has positively charged protons and neutrons that are bound within it. And then they are surrounded by orbiting electrons. Electrons have negative charge. This is the most fundamental of models that is still widely accepted today. Not until further research comes along and says something else is there. But this is the structure that you're familiar with. Electrons have negative charge. Protons have positive charge. Protons are bound within the nucleus, cannot move, cannot go anywhere. Electrons are orbiting. If they acquire sufficient energy, whatever form that energy takes, they could potentially leave that atom and go jump to another atom or leave the structure altogether and be free to move around. When they move, they carry their charge with them. When the charge flows, energy is moving, energy is transferred, and the rate of flow of charge is defined as electric current. So electric current, delta Q or delta T, or more efficiently, we can simply write dQ over dt. The time rate of flow of charge, dQ over dt mathematically, is defined as electric current I. And I has the unit of ampere. Okay. So charge is moving, charge is flowing, energy is being transferred. The amount of energy that is required to move one single unit charge, meaning one charge from one place to another, is defined as the voltage. Okay. And so we get delta W or delta Q. It's the amount of energy that is required to move it. Remember what I said. An electron can potentially acquire some energy. That energy could be in the form of thermal energy, could be form of electrical energy, but it can acquire some energy. That energy to move one unit of charge in 1 second is known as 1 volt or voltage. What is that lowercase w? What is it noting? The units are right there. Work, but what is it representing? Energy, joule, right? And so the rate at which work is done is defined as power. And here I would say rate at which work is done or energy is transferred is power. We can derive it, and if we derive it, we can find dW over dt as dW over dQ or charge, and then dQ over dt, rate of flow of charge. And so we get V times I. Electrical power is simply the product of voltage and current. E equals V times I. V times I. Units, James Watt equals volta times amperes. Use a more colloquial lingo, amps. Volts times amps. We have the broad classification of components or devices as either source or a load. So a source is a device that will always supply energy, and a load is a device that will always consume energy. Okay. If a device is supplying power, if it's supplying energy, it's a source. If a device is receiving or consuming power or it's consuming energy, it's a load. So one exception to this is your rechargeable battery. A rechargeable battery, when it is being charged, is receiving power. So it is acting as a source. And when you unplug it, the battery is now supplying energy to your device, and so it's now a source. The rechargeable battery can be both a source as well as a load. Yes. No dumb questions. That's actually a very good question. So the question being asked is, how would a battery know whether the energy is coming in or whether it's flowing out? And that ties into the fundamental. So if there is a load, it's going to pull energy from it, right? So if it's supplying energy, it's not a sentient being, so it doesn't know, right? So let's say you have a laptop. Anyone have a laptop with a removable battery? Anyone? Ever? No? All right, I had one. And so I still do, actually. 15-year-old, weighs about 8 pounds. It's got a removable battery, which itself probably weighs about half a pound. So you plug in the adapter in there, laptop works. If I remove the battery, the laptop is still going to work because there's a bypass mode in there. Okay. If I plug the battery in, if the battery, so there's a circuit in there that controls everything. So there's a power supply module and a circuit that controls everything. So once the laptop is plugged into the AC power outlet and a battery is plugged into the laptop, if it's not 100% charged, that module will send energy into the battery. So the module is the one that controls it. So the battery reaches full charge. It has a built-in chip that's going to tell the module, I'm full, I don't need any more. And then if I unplug the AC, so the power supply module is going to control the charging. Once it's full, it's going to stop the charging. That point, it goes into bypass mode, meaning the battery is bypassed and the AC power outlet goes directly into the laptop. I had one smartphone very early on, I might still have it somewhere, where it would be, you could plug in the phone, remove the battery, and the phone would still work because it had bypass mode. If you want to leave, you can leave. There's just one more thing I need to do. And so it's going to take me 1 more minute. So it's being recorded. If you have another class and you want to leave, that's fine. Energy follows law of conservation of, power and energy and everything follows the law of conservation of energy. So law of conservation of energy, everything must be balanced. If you look at our adapters, we never say that I have a 50-watt charger or I have we never say I have a minus 50-watt charger. I would only say I have a 50-watt charger. I would never put a minus sign. But the adapter is supplying power. So 50 watts coming from the adapter, it's going into my device. So my device is receiving 50 watts. Yet, if I need to mathematically balance my equations, I need to put a minus sign somewhere. So I put a minus sign where I'm supplying. So any device that supplies energy is going to have a minus sign in its power equation. So power is negative if it's a source, and power is positive if it's a load. Okay, so if it's an adapter or a charger, we say it's 50 watts, but mathematically, I would say it's minus 50 watts. My adapter supplies minus 50 watts equals my device, which is plus 50 watts. Sums up to 0. My equations are balanced. Law of conservation of energy is satisfied. All right, we'll end class here today. We'll pick up here on Wednesday. Please review the slides outside of class. If you have questions, feel free to ask at the beginning of next class.